Hey, everybody. So today we're looking at section 7.2. And in this screencast, I've decided I'm going to, instead of trying to do the whole section all at once, we're going to divide the section into two parts because it is pretty long. So with this first part, we're going to look at specifically the changing climate and our changing atmosphere and how those things relate to things like air pollution. And then the next day, tomorrow, you're going to look at part two, and that'll deal with other types of pollution and changes in the environment, including things like biomagnification and eutrophication. All right. Otherwise, I think this screencast will become like more than an hour in length. So we don't want to go there. So if you'll go ahead and start with the heading here, section 7.2, causes and effects of global change. And as you can tell by the heading, this is going to be a whole bunch of information. All right. So we'll just plan on that for this one. It's going to be a little involved because we're looking at global changes kind of in general. Okay. So make sure, again, you have the heading here. The objectives are kind of wide ranging for this section. So again, the ones that we're going to look at specifically are going to deal with the atmosphere, or the gaseous kind of composition that surrounds the earth and our biosphere. Okay, the land uses and different types of pollution leading to global changes will come into play more tomorrow with part two. Okay, so this is an image that was provided by the textbook. And what you maybe should see upon first glance of this is that this is real involved. Okay, we have a whole lot of stuff going on. We're looking at different causes of global change, and we have a lot of these things that are going to be human specific. All right, so in terms of those human specific items, we have things that are being circled right here. So we have changes in water quality, we have changes in air quality and the ozone layer and greenhouse gases over here. These are going to be kind of where we hang out for today. Well, we've already talked about a lot of these other items over here, how populations change and how that in turn can affect an ecosystem and its stability and levels of biodiversity. Soil quality, we talked about that with the nitrogen cycle and the phosphorus cycle, and so on. We have other types of abiotic things that are not necessarily human caused, but we know are present even in the absence of humans. So things like processes including photosynthesis and cellular respiration and evolution and circulation of atmospheric gases and something called the greenhouse effect. Up here, these are human-specific causes. So these are more like the negative types of impacts that we can have on our environment, especially what we see over here. And so you can read over those. All of these we'll be talking about at some point in this chapter. Okay, so when we look at this first slide of this section, in terms of what you need to write down, I would go ahead and really, I think the majority of this that you're seeing here is going to be important, which is kind of unfortunate, I know. But like I said, there's a lot of good information that's coming up here in this section. So I would make sure you go ahead and jot down these bullets as I talk about them. So when we talk about our atmosphere, we have concentrations of what we call greenhouse gases. And they're called greenhouse gases because if you know anything about a greenhouse, in general, they're going to be very warm environments. They're very conducive to plant growth. Usually lots of sunlight, lots of glass to allow that sunlight in, or plastic to allow that sunlight in. And so we get this term greenhouse gases from really that thing that we've created, the greenhouse that we use to grow plants. So we know that greenhouse gases in our atmosphere include at least three different types. These are the ones that are going to be present in the highest amounts. So we have H2O, and yes, I'm talking about H2O in the form of a gas, so that's water vapor. We have CO2, carbon dioxide, and we have CH4, which is methane gas. All right, and if you didn't know that CH4 is methane, I would make a note so that if you hear and see that word, you know what it is I'm talking about. All of these greenhouse gases, though, they sit up in the atmosphere, and they're there naturally. These are not things that humans have added up in the atmosphere. This greenhouse effect, as we're going to talk about, is something that's a natural property of the earth. So we know that in general, the more greenhouse gases we have, the warmer temperatures we see kind of globally, okay, worldwide. And the reason for that is because we have these gases that are really good at trapping re-radiated energy. Okay, and so I'll show you what that means here in just a second, I think, on the next slide, or not actually on the next slide. I've got a little video that'll go through that here in a minute. But when we look at these greenhouse gases, what they do, if we're talking about the Earth as a system and the sun's up here, when the sun solar rays reach the Earth's surface, some of that sunlight's going to be absorbed, especially by things like plants and algae that are going to do photosynthesis, but some of it gets reflected. And when that solar energy is reflected, it goes back up towards the atmosphere. But these greenhouse gases that sit up in the atmosphere will actually absorb the energy in their chemical bonds, and they convert it essentially into heat. So a greenhouse gas, water vapor, CO2, CH4, those three greenhouse gases are exceptionally good at taking that solar energy that's reflecting off the Earth's surface and turning it into heat. Okay, so in general, the more of those greenhouse gases you have, the warmer the Earth becomes, the warmer those atmospheric temperatures, and then in turn, the warmer, the land temperatures. Okay, so this whole process where these gases are absorbing that re-radiated energy is called the greenhouse effect. And it's not a vocab term, but I've got it in italics here because it is really important. So the greenhouse effect, like I said, this is a natural process. This is something that we see even without humans here on our planet. So it's something that I'm going to move my face around here so you can see the other one. It's something that would be here regardless of who is living on this planet. Okay. So what's important about that for us is that this is what actually allows the Earth to be what we call habitable, meaning living things can actually survive here. This is very different from something like the moon or from Mars or from Jupiter or other planets that are further away from the sun that lack that atmospheric kind of composition that we have here. So it's simply because of this greenhouse effect that we're able to survive on this planet. And so for that reason, it becomes really important for survival. Okay. Without it, it would be likely too cold to be habitable. All right. I'm going to pause here for a second. I'm going to show a video that'll talk about the greenhouse effect a little bit, but is also going to lead us into what we're going to talk about the next slide, which is climate change and global warming. Okay. So listen to the video, pay attention to where they're talking about, the relationship between the greenhouse effect and our greenhouse gases and climate change, because that's where we're going to come back. Okay. So 1 second.
Human activities, from pollution to overpopulation, are driving up the Earth's temperature and fundamentally changing the world around us. The main cause is a phenomenon known as the greenhouse effect. Gases in the atmosphere, such as water vapor, carbon dioxide, methane, nitrous oxide, and chlorofluorocarbons, let the sun's light in, but keep some of the heat from escaping, like the glass walls of a greenhouse. The more greenhouse gases in the atmosphere, the more heat gets trapped, strengthening the greenhouse effect and increasing the Earth's temperature. Human activities, like the burning of fossil fuels, have increased the amount of CO2 in the atmosphere by more than a third since the Industrial Revolution. The rapid increase in greenhouse gases in the atmosphere has warmed the planet at an alarming rate. While Earth's climate has fluctuated in the past, atmospheric carbon dioxide hasn't reached today's levels in hundreds of thousands of years. Climate change has consequences for our oceans, our weather, our food sources, and our health. Ice sheets, such as Greenland and Antarctica, are melting. The extra water that was once held in glaciers causes sea levels to rise and spills out of the oceans, flooding coastal regions. Warmer temperatures also make weather more extreme. This means not only more intense major storms, floods, and heavy snowfall, but also longer and more frequent droughts. These changes in weather pose challenges. Growing crops becomes more difficult. The areas where plants and animals can live shift, and water supplies are diminished. In addition to creating new agricultural challenges, climate change can directly affect people's physical health. In urban areas, the warmer atmosphere creates an environment that traps and increases the amount of smog. This is because smog contains ozone particles, which increase rapidly at higher temperatures. Exposure to higher levels of smog can cause health problems such as asthma, heart disease, and lung cancer. While the rapid rate of climate change is caused by humans, humans are also the ones who can combat it. If we work to replace fossil fuels with renewable energy sources like solar and wind, which don't produce greenhouse gas emissions, we might still be able to prevent some of the worst effects of climate change.
Okay, so hopefully that video gave you a little bit of an introduction into where we're going here, right? It certainly describes a whole lot about climate change and how that impacts our daily lives, whether or not we want to truly believe it and do anything about it yet. So what we know about this is that we understand, and as you saw in the video, atmospheric CO2 levels have been increasing for a long, long time, for several centuries now, and especially those in recent years, to the point where now we're over and above the threshold of where we've ever been, at least in terms of the data that we can obtain from geological samples. So we know that CO2 levels are rising. We know that that can be due to a lot of different things. But in general, remember, the more CO2 up in the atmosphere, the warmer the temperatures become. And then as a consequence of that, there's kind of a domino effect, like everything we've seen in ecology. You change one thing over here, you increase global temperatures, you're going to get stronger storms, you're going to get more droughts, you're going to get more wildfires, you're going to get lots of other things that as a whole impact kind of everybody globally. Okay, so when we talk about those changes that are occurring, we use the term climate change. Now recognize that that is different from this other definition I'm giving you down here for global warming. So climate change is the measurable long-term changes in averages of temperature, clouds, wind, precipitation, and frequency of extreme weather events. So this is long-term, okay, and this includes lots of different types of impacts, lots of different effects of simply raising that temperature. So we're looking at long-term scale. We're not talking about what happened last month, although that would be part of the data on the long term. We're looking at things from a broader perspective in the last decade or in the last 50 years and so on. Okay. And it also considers, again, like I said, not just changes in temperature. When you hear someone use the term global warming, or if you use the term global warming, you're referring specifically to temperatures, and that is it. Okay, you're not referring to extreme weather. You're not referring to natural disasters that would be caused by things like glacial melting. You're talking specifically about global temperature increase. So what we see in this picture here with annual Arctic sea ice in terms of the size of that over a period of time, we're looking at climate change over time. Okay, we're not looking at temperature in this diagram, although this would be an effect of that temperature, right? This would be dependent upon how that global temperature is increasing. So what you're seeing here is that throughout the course of the year, sea ice will grow when the Arctic region is in its winter months, when it's the coldest, and then towards its summer month, it shrinks, right? And so the amount of sea ice will decrease. So we're looking at here about 1978, 1980, all the way over here to 2015, which is about the time your textbook was written. So that was the last data piece that we have for this one. But you can see we have the growing and the retreating, and growing, retreating, growing, retreating, and so on. And it takes on that pathway. But the general trend line, I mean, if we had to fit like a best fit line to this data, would be something like that, right? So clearly we're decreasing over time to a significant point, even here, especially in like 2010, where we reached our lowest level. Okay. So all of that would be an indication of what we call climate change as due to global warming over time. Okay. Another thing that we see with increased levels of CO2 in the atmosphere is this process that we call ocean acidification. And we have seen this before. I think we talked about that as part of the carbon cycle, because this involves CO2, which contains carbon atoms. So we know in ocean acidification, again, if we put lots of CO2 up in the atmosphere, like I said, CO2 is great at absorbing re-radiated energy being reflected off the Earth's surface as part of that greenhouse effect. But we also know that the more CO2 in the atmosphere, the more CO2 in the air that surrounds us, the more likely it is that it also dissolves into ocean and large bodies of water. And what we know about these large bodies of water is that they function really well, actually, as what we call a carbon sink. So they're great at attracting CO2. They're great at dissolving that CO2 gas. But the problem that we have with that is that when CO2 dissolves into water, we get new types of chemicals and molecules that are formed. Okay, and I'll go ahead and say on this slide, if you want to kind of try and diagram this a little bit, I don't care that you diagram these molecules like exactly like they're being shown here, but maybe just the text might be important. Okay, you can certainly write out the chemical formulas like CO2 if you want, but you don't need to read and kind of draw all of these as you see them. Okay, so when CO2 dissolves into water, right, we have that over here. It'll actually kind of recombine with the molecule of water. Water is something that's attractive to CO2, and so those atoms and elements will kind of separate. And as a result of that, we get some hydrogens that add on to the CO2, and we add on the additional oxygen from water, and we form something called carbonic acid. Now, carbonic acid, being that it's an acid, has these extra hydrogen ions. And those hydrogen ions, one of the things that we define an acid by is the ability for it to lose and give away hydrogen ions. The better it loses those hydrogen ions, the more hydrogen ions it gives away, and the more likely it is to do that, the lower the pH. All right, and the lower the pH, the more acidic something becomes. Now, carbonic acid is pretty good at getting rid of hydrogen ions and losing them to the solution. What that means is that we're effectively decreasing the pH of our ocean water, which in turn, as you can imagine, is going to affect all the things that live there. Okay, so releasing those hydrogen ions lowers the pH, which in turn, I'm going to shift this around a little bit, which in turn is going to affect the living things there. Now, in addition to that, we have a second piece here. If we have dissolved CO2, let me make this one a different color. So if we have dissolved CO2 here, we have water here, and we formed carbonic acid, but now we've lost these hydrogen ions, right? These have been lost to the solution, and we're left with this carbonate ion. When those are formed in the solution, we can form two more bicarbonate ions, and as a result of that, that's going to take then a toll, not just on the ability of these things to survive in this environment, but also in order for some of these species to be able to actually produce things like shells that they need for protection and for survival. Let me erase some of this here so you can see what it says. So through this production of bicarbonate, what we end up seeing is we have lower pHs in these ecosystems because of the acidification process, because of those hydrogen ions being lost to the solution. And then as a result of that, those bicarbonates prevent shellfish and pteropods from actually making shells that they need for protection. Okay, and if they can't make body structures that they need for protection, then they're not protected. They're not going to survive well. And then you run the risk of things like coral reefs weakening and really over time bleaching. And as a result of that, entire ecosystems are at risk of just totally being wiped out. So this ocean acidification process is another consequence of adding more CO2 up in the atmosphere. It's not just now global warming that leads to climate change. Here now with ocean acidification, we have this additional component where now we're impacting water ecosystems. And it's not about, in this case, ice melting. This is looking at, how does that CO2 directly dissolve and impact those ocean ecosystems, regardless of what's happening global temperature wise. Okay. So this is in a number of ways, maybe more complicated than the greenhouse effect. But again, the bottom line is we're impacting these ecosystems, again, as another consequence of putting more CO2 up in the atmosphere. Okay. So moving on. All right. When we talk about ocean acidification, when we talk about climate change and global warming, all of this boils down to this idea of humans are putting more CO2 up in the atmosphere. Okay, and we know that CO2 is up in the atmosphere through burning of fossil fuels, which can also lead to pollution being added up into the atmosphere. And there's lots of different types of pollutants, but we know that pollution in general, and we should probably get the heading here too, can affect water, air, land. There's even a thing called noise pollution, which is like living in a big city, the amount of noise that's kind of constant there is something that can affect species behavior, natural things like squirrels and bird populations. Here again, we're focusing on atmospheric pollution, okay? So when we look at pollutant pollutants being added to the atmosphere or pollution up in the atmosphere, we know that these harmful effects from these types of chemicals can be immediate and occur very quickly, or they can be long-term and be very delayed. When we look at climate change and global warming, this in many ways is still a long-term type of process, right? This is something that has started for us in the last century and has been taking a while to kind of raise our temperatures. But now that we're getting that increase in temperature, it'll speed up a whole lot more quickly. Most common air pollution is going to come from burning fossil fuels, which again is called combustion. And that process releases several different types of pollutants up in the atmosphere, and we'll talk about what those are. But again, our fossil fuels, if you remember from the chapter, I guess chapter 4, when we talked about cycles, there are 3 of them that we mentioned. There's coal, there's oil, and then there's natural gas. Okay, so I would be familiar with those. When we burn coal and oil specifically, we form something called smog. And smog is probably something you've heard of, but this is a type of pollution that is produced that kind of looks like a smoky fog. And it's produced by the interaction of sunlight with pollutants. And there's 2 different types of pollutants specifically that we're looking at, and I'll show you those on the next slide. But these are called ground level particulates and ground level ozone. Okay, and we'll go through those here. Make sure you have really most of the bullets on this slide also. So when we look at those particulates in ground level ozone, and this first item up here at the top, you already wrote on the last slide, so you don't need to get that here. But these 2 I would definitely get jotted down, okay? So particulates are like tiny particles, okay? That word should hopefully remind you of the word particle, and when I think of particle, I think of teeny tiny things. So particulates are microscopic, 1 to 10 micrometers, okay? That's what that is, micrometers, not millimeter. It's 1/1000th of a millimeter. These are tiny, tiny pieces of dust and metal and unburned fuel. If you breathe them in as it sounds, it would not be a good thing. Okay, they can lead to more issues with COPD, emphysema, lung cancer, simply because asthma, simply because you're taking in, as you can imagine, microscopic bits of dust and metal and unburned fuel. It just sounds unhealthy, and it certainly is. So smog can be created if there are particulates hanging around here near the ground or in the lower atmosphere levels, and then the sunlight strikes those in a certain way to create what looks like the fog. The picture that you're looking at actually in the back of the screen has not been kind of faded out. That's actually what it looks like. And you can see kind of here at the bottom, here's the, whoops, let me go back. That was my mistake. At the bottom here, you can see, where we've actually got like what looks like a neighborhood here. And looking over that valley out in California, you can see that smoky fog. Okay. Ground level ozone is one type of air pollution that we tend to have issues with here in East Tennessee. And the reason for that is because there's a lot of combustion going on, not here in East Tennessee, but in places like North Carolina, in Georgia, in West and Central Tennessee. And because we sit in this valley, in this bowl, that air pollution kind of comes over and it'll just kind of sink and stay right here. So it takes a whole lot of effort really on the part of nature and wind currents to push that out. And that's why oftentimes in the summer we have like ozone action days or air quality alert days. It's because of not particulates, but ground level ozone, which is what you get from factories. So ground level ozone is O3. It's 3 oxygen atoms stuck together, covalently bonded. And this is formed when nitrous oxide, NO2, which is produced by combustion of fossil fuels, coal, oil, natural gas, reacts with oxygen in the air. So you've got these nitrous oxides that are produced that react with oxygen that's already present, and it makes O3, which is ozone. Ozone, we know at the level of the ground where we're just breathing it in and breathing it out is not going to be helpful for us. Okay, but ozone up in the higher levels of the atmosphere, towards outer space, towards the upper ends of the atmosphere, actually has a protective effect because its job there is going to be to actually help prevent some of those UV rays from striking the Earth's surface. And so up there, we like our ozone layer. And for a while, we had issues with the ozone layer, and I'll talk about that on the next slide. But ozone layer up above us is going to be very protective and helpful. It's the stuff at the ground that we're breathing in that can be super dangerous for health. And again, similar to particulates, can lead to higher incidences of health issues relating to lungs and breathing in the cardiovascular system. Okay. So that's our air pollution piece. I think I have one more slide. No, I have two more slides, it looks like. Okay, so when we look at air pollution, specifically those nitrous oxides that are released by combustion and also sulfur oxides, sometimes we get acid rain. So let's see. Let's do these three. You can skip maybe the shorter one here. So these come from, again, fossil fuel combustion. So there's that word again. We're burning that coal, oil, and natural gas. Acid rain is something you've probably heard of before, but acid rain is actually not something that you probably understand that well, because usually I think when we hear that term, acid rain, we're kind of confused because it's not exactly what it sounds like. So acid rain is produced when we have pollutants that cause the pH of rainfall or snow or sleet to drop below the normal level. Normal rain pH is about 5.6, which is actually already slightly acidic. If I move this picture down here, we can see what our pH scale actually kind of looks like. So normal pH is here at 7. All right, that's where we normally want to be in terms of like what we're consuming. As you go further in this direction, this becomes more acidic. And as you go further to the right, this is where we have our stronger bases. Okay, so anything below 7 is acidic, anything above 7 is basic. And for rainfall, we normally see something around here, about 5.6. That's our average rainfall. Acid rain, excuse me, can be anything around pH 4, 4.5, 5, anything that's slightly lower than that. So it's not this idea of like rain falling from the sky and burning holes in things. It's not that acidic, because if you look at our scale, orange juice is more acidic than acid rain. Lemon juice and vinegar are more acidic than acid rain. And so when we're talking about acid rain falling, I mean, you could imagine pouring orange juice on something. It doesn't like burn a hole in anything, but what it does do to ecosystems, and it can change the pH of water, bodies of water, similar to ocean acidification. It can make trees more vulnerable to disease and weathering, because over time it can lead to issues with leaf functionality. I was trying to think of that word, but the ability of leaves to do their job and do photosynthesis properly. So it can threaten water supplies, it can threaten those ecosystems, and it can harm trees and other plant life growing on the land if they're continuously exposed to acid rain. We don't tend to get a lot of acid rain around here, except for in the mountains. That is something that happens quite often there. Okay. Last slide for today, we're going to look at air pollution, specifically involving the ozone layer, that thing that I mentioned to you before, that's actually a beneficial layer and protective layer for us living here on the earth. So ozone layer, like I said, is beneficial to us. It helps protect us from specifically UV radiation, which is the same stuff we're trying to protect our skin from when we put on things like sunscreen. So UV radiation we know is carcinogenic, which means it has been shown to cause cancer. And so that's why we want to be protected from this if we can. CFCs are something that came out a while back and were kind of commercially used in refrigerants and coolants and other types of industrial products like that. And what we figured out in, I think it was the 80s, was that these CFCs can be really, really dangerous, especially for the ozone layer. So CFCs normally kind of sit up in the atmosphere, and excuse me, they're not just normally there, but when we use these, they will sit and they remain up in the atmosphere. So these things don't just kind of deteriorate and go away. What they do actually affect is the layering of that ozone. So these were banned based on some research that was done back in the 80s. They've since been removed from production, but we're still seeing kind of the consequences of that, what we had seen in the past. So these right here in this graph, you can see we've got ozone destroying halogens. Those are CFCs. And this is the concentration of those over a period of about a decade here, actually almost 2 decades. So if we look at the concentration of these back in the 90s, shortly after they were first banned, I mean, we have a huge concentration of these up in the atmosphere. And over time, since banning them, that's kind of dramatically decreased, and in a very positive way. So in a lot of ways, this is an example of how scientific research can be used to drive positive changes in our behavior and in our ability to kind of sustain our ecosystems. The same image over here on the right, you've got September 1981. This is showing the ozone layer as it was before, and then 87, just over the span of about 6 years. Here's the ozone hole. If you've ever heard of the hole in the ozone layer, this is that ozone hole expanding in just a 6-year period of time. Now that's since kind of reversed and is kind of reforming, which is helpful. But again, this shows kind of the impact of those CFCs and how dramatic that was and how important it was that we made some changes. So again, keeping in the positive kind of frame of mind with this, this is something that, again, we can hopefully use to promote more change in other things like climate change and air pollution in general. Okay. I have another video to kind of wrap up for today that's going to talk about CFCs and the ozone layer and what we've done and how that's been especially beneficial. And hopefully they describe it maybe in words that are better than mine on this one today. Okay. If you have any questions, let me know. Otherwise, I will see you for part 2 next time. All right. Bye, y'all.
15 dangerous radiation. Earth's atmosphere is made up of 6 layers. The second layer, called the stratosphere, contains the ozone layer. The ozone layer is made up of a highly reactive molecule called ozone, which contains 3 oxygen atoms. Ozone is a trace gas in the atmosphere. There are only about 3 molecules. A CFC is a molecule that contains the elements carbon, chlorine, and fluorine. CFCs are mostly found in refrigerants, aerosols, and plastic products. When CFCs are exposed to ultraviolet rays in the atmosphere, they break down into substances that include chlorine. The chlorine reacts with the oxygen atoms in ozone and rips apart the ozone molecule. Areas of damage in the ozone layer are often called ozone holes, but that name is misleading. Ozone layer damage is more like a thin 1980s. There, the region's low temperatures speed up the conversion of CFCs to ozone-damaging chlorine. About 90% of CFCs currently in the atmosphere were emitted by industrialized countries in the Northern Hemisphere. In 1989, the Montreal Protocol banned the production of ozone-depleting substances. Since then, the amount of chlorine and other ozone-depleting elements in the atmosphere have been falling. Scientists estimate that chlorine levels will return to their natural state in about 50 years. By then, the Antarctic ozone hole will shrink to smaller than 8 million square miles.